Okay. So today I'm going to discuss an opportunity for AI planning to tackle an important problem in power systems engineering, namely unit commitment. Unit commitment is an optimization problem which is integral to the secure, efficient and economic daily operation of a power system. I'll explain what the problem is, why the problem is important, and why AI planning can be a suitable method for solving this problem now and looking towards power systems of the future. My name is Josh Campion. I'm a postgraduate student at Durham University in the UK under the supervision of Dr. Chris Dent, and we're working in collaboration with Professor Maria Fox, Professor Derek Long and Dr. Danielle Magazzani of King's College in London. Okay, so first I want to introduce you to the traditional design of a power system, as in this schematic. So this is a power system which consists primarily of centrally controllable generators feeding power down through a network to customers. Now, as I said, unit commitment is an optimization problem, specifically scheduling which generating units will be on at what time in order to meet electricity demand over a given horizon. And that horizon is typically from now to 24 to 48 hours from now, and typically generating units need 4, 8, or even longer hours in order to come online. Economic dispatch is the name for an intrinsically linked subproblem. That is, finding the exact output for each generating unit for each time period that that generating unit is online. Economic dispatch is performed as part of unit commitment to assess the cost of a specific scheduling of generating units. Now, even though dispatch is calculated for the full planning horizon as part of unit commitment, in reality, the actual outputs of generating units are not set by their final unit commitment schedule, but by more complex economic dispatch algorithms run closer to real time. This means that the key part of a unit commitment solution is not the outputs of a generating unit, but the temporal online-offline schedules produced for each unit. Okay, so unit commitment is typically formulated as a mixed integer programming problem. So suppose our planning horizon is broken up into n time periods. Then for each generating unit in the system and each time period in that planning horizon, we have a binary decision variable representing whether the generating unit is online during that period, and a real valued decision variable representing the proposed output of that generating unit. Now we need to know the proposed output as we need to calculate a prospective cost. There is a cost for starting a unit up, another incurred for simply having a unit online, and a final marginal cost related to the output of the generating unit. The objective is to minimize the total of these operational costs throughout the whole planning horizon. There are many constraints needed to ensure that this model matches reality reasonably well, and these include things such as the maximum and minimum possible outputs of a generating unit, the minimum periods of time that a generating unit must remain online or remain offline once it comes online or offline, the amount by which a generating unit's output can vary between time periods, known as the ramp rate, and any commitments from previous planning periods which must remain in force at this time, as unit commitment is typically recalculated every 3 or 4 hours. So this is the bare bones of a unit commitment formulation, and as you can see, it's quite a large and complex optimization problem. Industry's accepted practice for this version of this problem is essentially by brute force. Parallel branch and bound on clusters of PCs can find a solution which is very accurate in an acceptable time frame. So if industry has an accepted method, then why are we talking about this today? Why is this a good opportunity for AI planning? Well, unit commitment is an extremely important problem to the power industry. The operational cost of running a power system for one day is huge, and with the rising prices of oil and gas, this cost is ever increasing. Coupling this with customer, political and regulatory demands for lower prices for customers has led the industry to an obsessive need to optimize every aspect of the system. Committing one portfolio of generating units for a day over another can have extremely expensive consequences for the cost of that day, and so ensuring the correct portfolio is chosen is imperative. Looking forward, there are more factors affecting unit commitment than ever before. In the next 10 to 30 years, we expect to see a very large increase in the amount of variable generation, such as wind farms and solar farms, integrated into the power system. This is non-controllable generation. It provides a source of electricity, but the amount and timing of production is stochastic and beyond the operator's control. We also expect to see much higher uptakes of smart appliances, electric cars, and other so-called controllable loads. These are customer demands for electricity, but where the system operator has some choice over when to serve those loads. Controllable loads allow a system operator to utilize the variable generation more effectively. A system operator can wait until the output from variable generation is realised and then serve any controllable loads with any excess renewable generation, rather than serving it immediately with expensive thermal generation. So together, controllable loads and stochastic renewable generation bring increased uncertainty to a problem which previously had very little, as customer demands have always been very well understood when aggregated out over a large network. This uncertainty is in the net demand, but it's also in the crucial temporal aspects of this problem. And finally, for this section, I'd like to highlight some of the shortcomings of the current methodologies. A mixed integer programming formulation has the difficulty of accurately representing customer demand, especially once wind power integration is considered, as this requires a reasonably fine discretization of time. Contrastingly, the time constraints on the minimum online and offline durations of generating units means that many generating units will be committed for most of or all of a day at one time, meaning their temporal scheduling is essentially fixed, whilst even peaking units will only come on at most 2 or 3 times a day. This means that most of the binary decision variables associated with the generating unit are fixed and become redundant once one decision about that unit has been made early on in the planning horizon. Reasoning about these excess variables unnecessarily extends the solution time for a branch and bound. The difficulty for many meta-heuristic methods which are tackling this problem is in randomly generating feasible solutions. The time spent generating these solutions and reasoning that they are infeasible reduces the benefit of a fast meta-heuristic over the more accurate branch and bound solution method, especially when the extra cost incurred through being further from optimality is considered. So these established methods come under further threats when we consider the difficulties introduced by future power systems as discussed earlier. The problem becomes much harder to model. Often the size of the model becomes intractable, and the uncertainty also contributes to the problem becoming intractable, and solution times for this problem extend beyond what is practically acceptable. So, while brute force and increased computing power will continue to be an option for solving this problem, there is a clear opportunity for a more flexible, scalable, and elegant solution method that's tailored for a problem of such temporal complexity. And our goal with this paper was to present a challenge to you as the planning community. That challenge is to produce a unit commitment methodology which is fast enough to be used in close to real time to achieve future power system goals of an autonomic power system, which is a power system that can respond on its own to changes in the network in real time. So we believe AI planning is a suitable choice in methodology for this problem, and having explained what the problem is, I'd like to spend the remainder of this presentation explaining why this is so through our thoughts on constructing an initial planning model. So our main drivers for using AI planning are as follows. There are far fewer times when a unit's online status switches than there are binary decision variables in a mixed integer programming formulation. AI planning has strong temporal reasoning, and if these switch points can be reasoned about effectively, then there should be a saving in the solution time here. We shall see shortly that the complex temporal constraints that meta-heuristics had difficulty handling can be replaced with 2 simple actions in an AI planning model. And finally, there is a clear separation of the temporal and numeric aspects of this problem, which we believe can be exploited effectively with a planning model. Okay, so now let's look at a model. So our first attempt involved modelling the deterministic version of this problem, so the original problem without the future power system difficulties. And we attempted to model this, the whole part of the problem, as a planning problem. So to represent the temporal schedules of the minimum online and offline periods, we have 2 simple actions, as I mentioned, a switch on and a switch off action. And these flip the predicates associated with the unit's online status. The switch on action runs for the minimum online period, the switch off action for the minimum offline period. 2 predicates, can switch on and can switch off, are then used to ensure that one of these actions cannot be interrupted by another for the same generating unit. And this easily enforces the temporal constraints and is a simpler formulation than the MIP model formulation and doesn't have the problem of generating the violating states as seen in many meta-heuristics. So to model individual unit output and total system supply, we have a fluent output associated with each generating unit object and a fluent supply. We then have 2 actions, ramp up and ramp down, which alter these fluents at a fixed rate per minute but with a variable duration. This allows the planner to set the value of any generating unit to any value and thus perform the economic dispatch subproblem. So to model demand, a discretized demand profile can be represented using a demand fluent and a series of timed initial fluents. We then use an envelope action to enforce the overall constraint of supply being greater than the changing demand. And finally, a system of predicates can be used to ensure that this action is scheduled over the same time period as the timed initial fluence altering the demand. So we attempted to solve this using the planner UP Murphy developed by Dan Magazzani and colleagues. The small systems of 2 or 3 units could be solved quickly, implying the concept and model were performing correctly. However, systems of 6 or 10 units stalled the search and prevented the problem from solving. A closer investigation of the states considered and search path taken showed that the planner could not distinguish between those solutions which only differed in the loading of the generating units. This means that despite having near identical online-offline schedules, which is the key part of the unit commitment solution, the planner could not distinguish between these states, and the sheer volume of them swamped the state space and prevented the problem from solving. It became clear that this approach was not going to be successful and that a different model should be tried. So if you recall, the key part of the unit commitment is the online-offline scheduling, not the exact loadings of the units which stall the search in the previous model. So if we return to the key actions in the model, you can see there is a clear separation between those representing the temporal aspects of the problem and those representing the numeric aspects of the problem. And we believe we can exploit this structure to prevent the planner from stalling over similar solutions. So by removing the economic dispatch subproblem and delegating dispatch to a linear programming model leaves only the temporal side of the problem for the planner to consider. In principle, this is simple, but in practice there are many complications to overcome. So if we return to the model, the switch on and switch off actions remain essentially unchanged. For balancing supply and demand, the envelope action remains much the same. However, now only the maximum total supply of all the generating units which are online is required to be greater than the demand, and there's a large payoff in doing this. The near infinite number of branching possibilities stemming from reasoning about the frequency and duration of the ramping actions, which set the value of the exact supply and output fluence, is removed in favour of a single maximum supply fluent, whose value is determined entirely by the switch on and switch off actions. So the purpose of setting the exact values of that fluent was to calculate a least cost, and that is an optimisation problem. The planner spent much of its time focusing on that problem, and that wasn't its strength. So by removing the need for the planner to consider the subproblem, we free the planner to spend its time reasoning on the crucial temporal aspects of the problem. So the key to success now lies in integrating this linear dispatch model. So the key responsibilities of this model are to take the temporal schedule produced so far, check the feasibility of the state with more complex constraints than can be modelled in PDL, and to calculate the cost, the lowest expected cost, which is then fed back into the planner to be used as part of the metric to help guide the search. So by delegating optimization, we see that the planner deals with a much simpler version of the problem and receives guidance on optimization. And we believe this is the key to extracting performance and optimality from an AI planning approach. So the open problems for this model are to develop a heuristic which is accurate enough to be representative of the problem, but relaxed enough to be solved quickly. How to inform the search about helpful actions, where typically it's not which actions to perform next, but when to perform those actions that is important. And how to schedule actions based upon the timed initial fluents which are altering the demand, as these provide the key decision points for this problem. It's not a case of reasoning about which actions to perform in order to achieve a set of goals, but which actions to perform in order to ensure certain facts remain true in a changing environment. And finally, how to efficiently integrate the LP without costing excessive time, both in its solution and in communication with the planner. So to conclude, we believe that a separated AI planning model with reduced knowledge of the full problem that delegates heavy optimization to an external solver can produce a unit commitment methodology which is capable of levels of optimization which are closer to branch and bound, but with the short solution times of the meta-heuristics in the literature today, making it a suitable candidate for the above challenge. So we hope you enjoy thinking about this problem and look forward to discussing any questions you may have. Thank you for listening.